Imagine for just a second that you were running the door at, like, the most exclusive high-traffic nightclub in the entire world.
Okay, well, that sounds stressful already.
Right. But there is a massive catch here. You have to check the ID of every single person who wants to come in or leave in less than a microsecond.
Oh, wow. Good luck with that.
Yeah. And one more thing. Every time you blink, you get complete amnesia.
Wait, what?
You forget everyone you have ever met. Even the person you just let inside a split second ago, completely gone from your memory. So how do you possibly decide who gets in and who gets blocked?
I mean, it sounds like an absolute nightmare scenario for running a nightclub. But that amnesiac bouncer actually forms the bedrock of how we secure modern computer networks.
Welcome to the WeCyberYou Unlocked podcast. And just a quick reminder, if you are new here, go ahead and hit that follow button and definitely visit WeCyberYou.com for more deep dives into the tech that runs our world.
We've got some great stuff on there.
We really do. But today, our mission for this deep dive is to figure out how this flawed, forgetful technology, which is known as the Packet Filtering Firewall, or the stateless firewall, how it still acts as the invisible bouncer for networks worldwide.
And it is an incredibly critical topic to explore for you listening, because the stateless firewall is, well, it's one of the earliest firewall designs out there.
Right.
It operates primarily at what we call the OSI network layer, which is layer 3, and the transport layer, layer 4.
Which sounds super old school.
It does. It might sound like ancient history in internet years, but it is far from obsolete. You really can't grasp how modern, complex cybersecurity works until you understand the raw mechanics of this foundational layer.
Okay, let's unpack this, because before we can figure out how this firewall stops threats, we need to understand exactly what it's looking at, right?
Absolutely.
We throw the word data around constantly, but for you listening right now, when you send an email or load a web page or even just stream this audio, that data does not travel across the internet in one giant solid block.
No, not at all.
It gets shattered into, like, thousands of tiny independent units called packets.
That's a great visual.
Mm-hmm.
I mean, on your end, your device reassembled everything so the audio plays smoothly. But out in transit on the internet wires, it is just a chaotic, high-speed stream of these fragmented packets.
So imagine a single packet as a physical letter you are dropping in the mail. That letter has two distinct parts.
Okay.
First, you have the envelope itself. That has all the routing metadata on the outside, the return address, the destination address, the zip code. We call this the header.
Right, the header.
Then you have the actual letter folded up inside the envelope. That's the information you actually care about reading. We call that the payload.
And that analogy maps perfectly to the technology. And this really brings us to the crucial limitation of the stateless firewall.
Which is?
It only looks at the outside of the envelope.
Just the header.
Just the header. It does not care at all about the payload inside. It simply will not open the envelope to see if the letter contains a friendly greeting or, a malicious computer virus.
So it's totally blind to the contents.
Completely blind. I mean, it is making its entire security judgment based strictly on the routing information printed on the outside.
Okay, so if it is, like, legally blind to the actual letter and can only read the envelope, how is it deciding what to do with it without slowing down the entire digital mailroom?
Well, it uses something called an access control list. You'll usually hear it referred to as an ECL.
Ah, so this is the bouncer's clipboard.
Spot on, the clipboard. These firewalls usually sit right at the boundaries of a network. Think of it like the perimeter routers connecting an office building to the broader internet.
Okay, yeah.
They are armed with this ACL, which is essentially a really rigid, predefined rulebook. As each packet arrives, the firewall checks the header against a specific set of criteria.
I want to make this tangible for the listener, though. What exact metadata is it pulling off that envelope?
So it looks at 4 main things. First, where is the packet from? That's the source IP address. Second, where is it going? That's the destination IP. Third, it checks the source and destination ports.
Let's pause on ports for a second, because that definitely trips people up.
It does, yeah.
If the IP address is, say, the street address of an apartment building, the port is the specific apartment number inside, right?
That is a brilliant way to frame it. So a server has thousands of these apartment doors or ports designated for different services.
You mean example?
Sure. So if you are browsing the web securely, that traffic is expected to go to port 443, which handles HTTPS.
Got it.
But on the other hand, it might look for traffic headed to port 23, which handles Telnet. And Telnet is a very old, unencrypted, and highly insecure protocol.
Right, we don't want that.
Exactly. And finally, the fourth thing it checks is the protocol type itself. Is this a TCP connection, a UDP stream, or an ICMP ping request?
Okay, let's do a quick ELI5 explain protocol. Like I'm 5 on those protocols, because that alphabet soup can get confusing fast.
Fair enough. So TCP is like sending a certified letter.
Okay.
The sender and the receiver have to verify delivery. It is highly reliable.
And UDP?
UDP is more like a paperboy throwing a newspaper onto your porch from a moving bicycle.
Nice.
You hope it gets there, but nobody is stopping to check signatures. It's used for things that need to be fast, like live video streaming.
And the last one? ICMP.
ICMP is basically just a sonar ping. It's one computer saying, "Hey, are you awake?" and the other replying, "Yes, I am."
So the firewall is reading these metadata fields, the IPs, the ports and protocols, and running them through a logic tree. And looking at our notes for this deep dive, that logic tree is shockingly simple.
It really is.
It processes top down, like
Sure.
this. Rule number 1, does this envelope match an allow rule on my clipboard?
Yeah.
If yes, forward it, open the door.
Exactly.
If it didn't match an allow rule, we move to step 2. Does it match a deny rule? If yes, drop it into the trash. And step 3, what if no rule applies at all? Then you hit the default policy, which in any secure environment is going to be a default deny. When in doubt, kick them out.
You have the exact workflow there. To give you a concrete example from the research, an ACL rule set might literally read, Rule 1, allow TCP traffic from any IP address to port 443.
Which lets normal, secure web traffic into the building.
Right. But the next rule might say, Rule 2, block all traffic to port 23. That shuts down anyone trying to use that insecure Telnet protocol.
Okay.
A third rule could say, Rule 3, block all ICMP traffic from the outside. That stops external hackers from pinging your network just to map out which computers are currently turned on.
The firewall just goes down this list rule by rule, top to bottom. And honestly, if you're listening to this right now on a cell connection, your packets are passing through a stateless ACL at your provider's edge router, literally millions of them a second, just to get this audio to your device.
The sheer volume is staggering. And because it is only checking metadata against a simple text list, decisions are being made in a fraction of a microsecond.
See, here is where I have to push back a bit.
Okay.
Because in technology, speed almost always comes at a massive cost. Processing millions of packets in microseconds is phenomenally fast. What corners is this firewall cutting to achieve that kind of velocity?
The corner it cuts is memory, which brings us to the core concept of why it is called a stateless firewall in the first place.
The amnesia problem.
Exactly. The defining characteristic of this system is that it maintains zero state. It has no memory of past events.
None at all.
None. It does not track active connections. It doesn't understand login sessions or web browsing flows. It doesn't maintain a connection table of who is talking to whom. Every single packet is judged in total isolation.
Why is memory such a bottleneck, though? Why not just give the firewall a little bit of RAM so it can remember what it did like a second ago?
Because memory tracking is incredibly computationally expensive. For a firewall to remember a conversation, which is what we call stateful inspection, it has to create a massive spreadsheet in its active memory.
Like a ledger.
Right. Every time a new connection starts, it writes down, computer A is talking to server B on port 443.
Okay.
For every single packet that arrives after that, the firewall's processor has to pause, search that massive spreadsheet, find the matching entry, verify the context, and then make a decision.
Oh, wow.
Doing that for 10 million packets a second requires massive, expensive processors and huge amounts of RAM. A stateless firewall skips the spreadsheet entirely. It just looks at the clipboard, looks at the envelope, and says yes or no.
Okay, that makes sense from a hardware perspective.
Yeah.
But from a functional perspective, I want to make sure you and I are on the same page and that you, listening, can visualize the real-world consequence of this.
Sure, let's do a scenario.
Let's say I try to connect to my bank's secure website.
Okay.
I send a packet out from my laptop saying, hey, let's start an HTTPS connection. My stateless firewall looks at the envelope, sees port 443, says, okay, that's allowed, and sends it out.
Yep, so far so good.
The bank server gets it and replies with my encrypted account data. That return packet hits my firewall. Are you telling me the firewall looks at the returning data and goes, who are you? I've never met you. Because it literally forgot my initial request, sent a millisecond ago.
What's fascinating here is, yes, that is exactly what happens. It evaluates that return packet entirely on its own merits, completely blind to the fact that you just asked for it.
That seems like it would fundamentally break the internet. I mean, if it forgets I asked for the data, how does the bank's reply actually get back to my laptop?
It requires incredibly careful and honestly sometimes risky configuration by network administrators.
How so?
Because the firewall doesn't remember outbound requests, the administrator has to write a permanent rule on the clipboard that says, allow all inbound traffic from any high-numbered port just to ensure return traffic can make it back through.
Wait, but by opening up all those ports permanently, you are leaving massive holes in your defense.
Yep.
You are essentially telling the bouncer to let anyone in, as long as they were wearing a certain color shirt, without verifying if they're actually part of the party.
It is a massive structural weakness. You might allow inbound packets without ever verifying the context of the conversation.
So if this technology has total amnesia, and it only looks at the outside of the envelope, it must be incredibly easy to fool. Let's get into the fatal flaws here. If I'm a hacker, and I know you are running a stateless firewall, how am I exploiting those blind spots?
Well, the most obvious method is IP spoofing.
Okay, let's break down the mechanics of that. If the firewall literally doesn't remember a packet from a microsecond ago, and it can't look inside the envelope, couldn't an attacker just grab a pen and write a fake return address on the outside of the envelope?
That is exactly what IP spoofing is. In a more advanced stateful system, the firewall watches the entire TCP handshake, that certified mail process we talked about earlier.
Right.
It watches the two computers actively verify each other's identities before opening the door. But a stateless firewall doesn't track handshakes.
Because it has no memory.
Right. It just looks at the return address field of the header. If the hacker alters their packet header to say, I am coming from the CEO's trusted internal IP address, the stateless firewall has no mechanism to verify if that is true.
It just looks at the fake name tags, says, welcome back, boss. It waves them right through.
Absolutely. It just waves them through. But the flaws get much worse when we talk about what is hiding inside the envelope.
Oh, right, the payload.
Because there is no payload inspection, a stateless firewall is completely oblivious to application layer attacks.
Like in SQL injection.
Exactly. Let's explain what that actually looks like to the firewall. An attacker decides to target your customer database. They craft a standard web request addressed to your web server on port 443.
Okay.
The stateless firewall checks the header. Destination port 443, that's our web server. Allowed. It forwards the packet.
But it never opens the envelope to read the letter inside. And the letter inside doesn't say, please load the home page. The letter says, command, delete the entire user database.
And by the time the database server reads that malicious payload, the firewall has already gone back to checking the next packet.
Wow.
It is equally blind to cross-site scripting or XSS attacks, where hackers embed malicious code into web pages to steal user data, or malicious API requests, or actual destructive malware hidden right there in the payload.
Because of this, stateless firewalls are basically useless against advanced persistent threats, APTs.
Totally useless.
These are the sophisticated, slow-moving attacks, often state-sponsored, that sneak into a network and quietly spread over months. Because APTs format their communication to look like standard, allowed traffic, the amnesiac bouncer never suspects a thing.
They just do not possess the intelligence to spot automated exploitation tools that are, technically speaking, playing by the structural rules of the network, but carrying highly dangerous cargo.
Okay, that is a fairly brutal indictment.
It is.
It is blind, it has no memory, and it can be tricked by a teenager with a fake digital ID. So I have to ask the obvious question. Why on earth haven't we thrown it into the dustbin of computing history?
That's a fair question.
If it is so deeply flawed, why did you say at the beginning that it remains a vital building block? Let's balance the scales here. What are its undeniable strengths?
Well, consider the alternative. If you try to deeply inspect every single piece of data hitting your network will literally grind to a halt. The advantages of the stateless firewall all stem directly from its simplicity.
Okay.
Because it isn't doing heavy memory tracking and it isn't opening envelopes to read payloads, its resource consumption is almost zero.
Oh, so it doesn't need a massive power-hungry processor or expensive RAM to do its job?
Right. And because it operates on a straightforward text-based logic tree, it is incredibly easy to configure.
No PhD required.
Exactly. You do not need a team of high-level security analysts to set up a basic access control list. Furthermore, It is incredibly cost-effective.
Which companies love.
Whoa, they love it. You don't have to buy a dedicated $50,000 security appliance to get stateless filtering. This capability is usually built natively into the basic routers and network switches a company already owns.
So it basically serves as the ultimate triage tool. It's cheap, it's lightning fast, and it weeds out 90% of the obvious internet background noise, the automated scanners, the bulk ping requests, without breaking a sweat.
That's it. It handles the sheer volume of noise so your expensive equipment doesn't have to.
So for you listening right now, if you look around your home or your office, where is this fast but flawed technology actually operating at this very second?
Oh, you are almost certainly using one right now. The basic filtering on your home Wi-Fi router relies heavily on stateless packet filtering to block random inbound internet traffic.
Makes sense.
Embedded systems and IoT devices, think about the smart thermostat on your wall, or a connected baby monitor, they often rely on stateless filtering because their tiny internal chips just don't have the computing power for anything heavier.
And what about in massive corporate environments?
In the corporate enterprise world, you will find stateless firewalls acting as the primary perimeter ACLs on massive, heavy-duty network switches. They sit at the very edge of the corporate boundary, absorbing and filtering massive volumes of raw traffic from the open internet.
Just swatting away the easy stuff.
Yep.
And this is the absolute key to modern cybersecurity architecture.
Yep.
You never, ever use a stateless firewall alone anymore.
Never.
Because if you do, you are leaving your servers wide open to that SQL injection bomb we talked about earlier.
Exactly. If we connect this to the bigger picture, modern security is built entirely upon the layered defense concept.
Okay.
The stateless firewall is just the outermost wall of the castle.
And this is where it gets incredibly cool. Because looking at our deep dive research, the stateless firewall isn't working alone. It is backed up by an absolute all-star team of security tools.
It really is.
Let's run down the gauntlet. If a malicious packet somehow sneaks past our fast amnesiac bouncer at the front gate, what does it run into next?
The very next layer it hits is usually a stateful firewall.
Ah, the bouncer that actually remembers faces.
Right?
The stateful firewall creates that memory spreadsheet. It tracks active connections, so it knows if you actually requested that returning web page, and it will only let the reply back in if it matches an open session in its memory.
But remember, even a traditional stateful firewall might not open the envelope. It just verifies the flow of the conversation.
Which is why the packet then hits the next generation firewall, or the NGFW. These act like the heavy-duty security guards. They actually open the envelope.
They do. They perform deep packet inspection, look at the payload itself, and understand application behavior to see if the letter contains a virus.
And it doesn't stop there.
No, we can take it even further. Depending on the environment, the traffic might then pass through a web application firewall, a WAF.
The WAF is essentially a highly specialized bodyguard assigned specifically to protect the web server. Right.
Spot on. It operates all the way up at layer 7, the application layer scanning for those complex SQL injections and cross-site scripting payloads that the stateless firewall was blind to.
Plus, you also have intrusion prevention systems, or IPS, acting like digital detectives.
Yes. They actively scan the network traffic against a massive, constantly updated database of known criminal fingerprints, looking for exploit signatures.
And sitting over all of this, directing traffic, we increasingly have zero-trust architectures. The philosophy there is that absolutely no one is trusted by default, regardless of whether they are sitting outside the network in a coffee shop or plugged directly into the wall inside the corporate headquarters.
You have to prove who you are at every single step.
When you look at that entire ecosystem, the role of the stateless firewall makes perfect sense. It thins the herd.
That's the perfect way to put it. You do not want your highly advanced next-generation firewall wasting its expensive CPU cycles dropping basic automated ping sweeps from the internet.
Right.
You let the fast, cheap technology handle the massive bulk of the traffic at the perimeter, saving the heavy computing power for analyzing complex targeted threats deeper inside the network.
It really is a gauntlet. I mean, you have to survive the fast bouncer, then the smart bouncer with a memory, then the deep cover investigator checking your luggage, and finally the bodyguard at the VIP room.
And the stateless firewall is just the guy on the sidewalk checking for a ticket.
Just checking the ticket. It does one specific job, and it does it at blistering speeds.
It does.
Let's bring this all together for you. The Packet Filtering Firewall, the stateless firewall, is the speedy, lightweight amnesiac bouncer of your network.
Yep.
It is entirely rule-based, using an access control list. It only looks at the routing metadata on the outside of the envelope, and it completely lacks the intelligence or the memory to spot modern complex threats on its own. But because it is so incredibly fast and cheap to run, it remains a vital load-bearing pillar in a much larger layered security strategy.
It is the ultimate proof that sometimes doing a very simple task very quickly is exactly what a complex system needs to survive.
Absolutely. Well, thank you so much for taking this journey with us today on the WeCyberYou Unlocked podcast. As always, please hit that follow button on the channel, and do not forget to visit WeCyberYou.com for more deep dives into the technologies shaping our world.
And before we go, consider this provocative shift happening right now.
Okay.
As modern internet traffic becomes increasingly encrypted end-to-end, meaning the payload inside the envelope is mathematically locked and hidden from almost everyone in the transit chain, including our own advanced firewalls.
Right.
Does the outside of the envelope suddenly become our most valuable source of truth once again? Even as we build incredibly advanced, deep inspecting security tools, are we slowly returning to a reality where we are forced to judge a packet entirely by its cover?